Back in episode 4, I threw out the notion of population center. To my mind, the population center is the point in two-dimensional space smack in the middle of where we found a bunch of mussels belonging to a particular species. It's kind of like density, and it's even based on the same raw GPS data. But to me, density is about how tightly packed mussels are, while population center can give us a notion of where the critters are located geographically. If we were talking about people in a city, we might use population density to compare a suburb to a high-rise apartment building. Population center might help planners to determine the best location for maybe a new park or a BVM branch. Back to our mussels, if we can determine a population center for a given roundup, we'd have a single point to compare to other roundups, and so maybe find interesting shifts in population in position of the mussels as a group. Let's illustrate this with an example. Say we found 3 mussels on a simple grid. The one on the left is located 1 meter from the left and 1 meter down from the top. The middle one is 8 from the left and 6 from the top. And the one on the right is 13 from the left and 2 from the top. I adapted a formula that engineers use to find the center of gravity of an object in this situation. The engineering method first multiplies the weight of each object times its distance from 2 baselines to get something called moment. Then the formula divides the total moment by the total weight. Do this in both directions and you've found the center of gravity. Instead of mussels, let's assume that our 3 objects are, checkers. And they each weigh exactly a gram. The first step is to create a table for the x values. The left-hand object weighs a gram and is 1 meter from the left. Multiply 1 times 1 and you get a moment for that object of, 1. The second object is 1 gram times a distance of 8 to give a moment of 8. 1 times 13 is 13. The total weight winds up being 3, and the total moment is 22. Engineers use this formula, where total moment divided by total weight gives the x-coordinate for the center of gravity. When we stick our numbers in that formula, we get an x value of about 7.3. Do the same thing in the up and down direction to get the y-coordinate. In this case, it's 2.7 meters from the top of the grid. So there you have it. The little orange dot represents the center of gravity of the little blue dots. I've chosen to adapt the engineering method for center of gravity to find the center of my mussel populations in 2 dimensions. To keep things simple for the time being, I'm going to substitute number of individuals for weights. I'm assuming for now that a small adult mussel is just as important as a large adult mussel. It's common to find 2, 3, or even more mussels right next to one another out there in nature. And our little method here allows us to account for that clumping phenomenon. Here, I've left the locations the same, but now there's 4 mussels on our grid. 2 of them are in the 1, -1 position in the upper left corner. As you can see, throwing that 4th mussel into the mix changes things. Now at that first location, we've got 2 individuals times a distance of 1 for a moment of 2. That changes the totals of individuals and the total moments. So the population center, that little orange dot, shifts a bit up and to the left. I put this math to work by creating a spreadsheet that converts latitude and longitude coordinates into meters. The details are beyond the scope of this presentation. Suffice it to say that telling the computer the GPS coordinates allows it to calculate the distances in meters from baselines to the west, northwest, and the north-northeast of the mussel bed. For example, point C here is latitude 642 and longitude 307. The computer places that on an XY grid. 61.1 meters from the left and 13.9 meters from the top. Here are those baselines inscribed onto a satellite image. The north-northeast baseline generally follows the trend of the shoreline, and the one to the left is perpendicular to it. Our hypothetical point C is shown here. Now we can rotate that satellite image a bit counterclockwise so that it lines up nicely with the computer-generated graph. The beauty of this spreadsheet-generated graph is that it'll rapidly convert masses of GPS data into useful plots on a meter-by-meter grid. Those data can then be used to find the mean and standard deviation values in both directions. For example, here's the population center for the Silicoidea we found during the 2021 summer roundup. One way to express this in words would be to say that the Silicoidea's population centered a little over 100 meters from the left of the bed and around 13.5 meters from shore. The population center for Subrostrata is just a bit left of that for Silicoidea and the same distance from shore. The center for Pyganodon grandis, however, is quite a ways to the right of the previous two species, on the order of 40 or 50 meters. It's also a bit farther from shore. The population center for Elliptio fell somewhere between Silicoidea and grandis. In case that went a little fast, here's a summary of what we just saw. In terms of distance from the western baseline, the population centers for Silicoidea, Subrostrata, and Dilatata all fell pretty near one another, while the center for grandis was way off to the east. Also, grandis was centered several meters farther from shore than the other three. Now, whether these differences will stand up to statistical testing remains to be seen. This really kind of starts to get fun when we start comparing apples to apples. So when we look at the scatter plot for Lampsilla silicoidea during the summer of 2021 versus summer of 2022 roundups, they are kind of similar and kind of different. So looks to me like maybe we had a little broader distribution of dots during summer 2021, and then this year maybe a little bit tighter and a little bit farther to the east. But honestly, it's a little bit hard to compare scattery blob-like shapes, and that's why I chose to use this population center metric as a way of maybe getting a little more precise about that. And as promised, here it is. We look at the same species again, Silicoidea, in a year apart, 2021 and 2022. And my gut feeling is kind of borne out here by the math. It does look to me like during 2021, the population center was a little bit farther west, maybe 25 meters or so west of where we found it to be in 2022. So in other words, the center of the population seems to have shifted to the east somewhat from one year to the next. And also, if you look at the north-south, you know, the y-axis, there's a little bit of a difference between the 2 years. So in 2021, population centered about 13.5 meters from the north baseline, and was a little bit farther to the out into the lake, maybe half a meter or so. I don't know how much stock to put in that. It's not very far. And also, as you know, the shoreline trends. It's not exactly straight, so you know it's kind of something like that. So if you had a little bit of an east shift, you might expect to see a little bit of an offshore shift as well. But as I said, I'm not going to put too much emphasis on that at the present time. But it is kind of interesting to see that we did see a change in the center of the population, a little bit shifted toward the east. And we'll leave it right about there for the present time. I could go through and compare all the different other species between 2021 and 2022. I could compare the distributions of species within 2022, one to another, but I'm not going to do that right now. I've got plenty of other fish to fry down the road. We'll do some of those comparisons in the future, including looking at mussel roundups from past years before 2021. Until next time, take care. Bye.